This might just be the worst printer I've ever used. And this is the type head from an IBM Selector 2 typewriter. Now, for those of you who are too young to remember, typewriters are what we used to use to write everything back before computers. I mean, we did write some things by hand, but who can read this sort of handwriting? But of all the typewriters ever made, the IBM Selectric is by far the most interesting to me. And I'm not just saying that because I like overly complicated mechanical devices. Wait, what was that you're saying? Oh, sorry, I am just saying that because I like overly complicated mechanical devices. I mean, seriously though, the service manual for this typewriter is over 240 pages long. And not only that, but they managed to squeeze all the characters you could ever need onto a type head the size and shape of a golf ball. And not just one ball either, but they made over 50 different fonts for this. Which, all put together, leads to what is probably the world's greatest typing experience. Or at least I'd really hope it was. Back when this was released, a new IBM Selectric cost over $3,500 of today's dollars. However, what I actually want to do is to use this type ball to print pictures, which is something the entire system was never designed to do. Now, I could just automate an existing typewriter, but where's the fun in that? Instead, I'm going to build my own fully custom computer-controlled typewriter using this type ball from the Selectric typewriter. And this leads to our first question. What does a typewriter actually do? I mean, we all have a general idea of it. You press a key, it makes a thwacking sound, and then a letter appears. Once that letter's on the page moves a bit to get you ready for the next letter. Now this gives us two goals that our typewriter must accomplish. First, it needs to print a character on the page, and then second, it needs to move that page to get ready for the next character. So let's start with my first goal, making the character appear on the page. The classic way to type a character is to have a type element, like this one here, which is effectively a stamp with the shape of the letter we want on it. And this will be at the end of a long rod. When the key is pressed, the rod flings the type element at the paper quite quickly. But a stamp by itself won't produce a mark on the paper, and to do that we need some sort of ink. Typically a typewriter would use an ink ribbon, just like this one, placed between the type element and the paper. And so this is exactly what I'm going to do on my typewriter. Now that the ribbon's in place, we can print a letter. Well, there's one important thing that I haven't mentioned yet. Where's the power for all this motion coming from? Now, in a fully mechanical typewriter, the power comes directly from your finger pressing the key. Now, more advanced typewriters, such as the Selectric itself, would have an electric motor to assist this process, but it's still your finger that gets it all started. Since I'm building this typewriter to be entirely computer controlled, I can't rely on my finger just pressing the key every time I need to make a character. I mean, I guess I could do that. I don't want to do that, though. So I need some sort of electric actuator. That's where the solenoid comes in. When I apply power, it will fling this whole assembly towards the paper. Thanks to the long shaft, the type element will be moving pretty fast, and hopefully that'll be fast enough to produce a good character on the paper. And if all we cared about was a single character, we'd be done. But I would like to have the entire alphabet to work with. I mean, I could just duplicate this arrangement once for each character. And in fact, that's pretty much how all typewriters work, with a separate lever and type element for each character. And this is what I find really cool about the Selectric. All the characters it had were on this one type element. Now a ball like this one I have here has 88 characters in total, organized into 4 rows and 22 columns. Of course, it has the 26 letters of the alphabet, in both lower and upper case, and the digits 0 through 9. But that's only 62. There's still another 20 characters left. Now most of these are pretty standard punctuation and symbol characters, but there's a couple in there that we don't normally see on a keyboard these days, such as the degree symbol, plus minus, and the cent symbol. Now it is worth noting that the character set wasn't standard across all type balls. In fact, they made some type balls that were nothing but symbols. Of course, this would mean that the characters on the keyboard of the typewriter didn't always match what was on the type ball, so an experienced typist would just have to learn what went where. Now for me, this means I'll need to have some mechanism to tilt the ball forward and back, and to rotate it to allow me to select the right character. I'll start with the rows. To select a particular row, I need to tilt the ball forward and back somehow. Now, the Selectric uses the rotating shaft and a pair of bevel gears to achieve this motion. But I'm going to go with something a little bit more modern, a servo. A slightly smaller servo. And I'll attach it to the mechanism down here, pretty far away from everything. And then I'll connect it to the tilt plate using a push rod. And with that, I've got the row selection working. Now I just need to rotate the ball between all the columns. And this is no problem. Since I need to rotate it 360 degrees, I'll just use our old friend, the stepper motor. I've added a magnetic encoder to this one, so we'll always know exactly where it is. Since the motor is actually bigger than the ball, I can't put it inside the ball. So instead I'll put it here, right at the pivot point of this arm. And I'll run a shaft up from the motor to the ball. And so that's it, right? Well, you might have noticed one problem with this. The shaft I just added will keep the ball from tilting, which is a problem. So I popped open the Selectric service manual to see how they solved it. Now you see that tiny part right there? That's called a dog bone, and it's such a simple solution. It's really just a small piece of metal with a cutout on each end, which makes it look sort of like a bone, hence the name. Each slot rests on a pin, one side on the ball and the other side on the shaft. Since the pin is free to slide in the slot, it allows the ball to tilt while still letting us control the rotation of the ball. Here I've cut the model in half so you can see what's going on. And so, as you can see, I just copied this directly to my version. And with that, we're able to select any character we want from the type ball, and then we can print that character on the paper. Of course, we don't want to print all of our characters in the same spot, and I'd rather not have to move the paper manually. Remember, computer control. So I'll build the machine to do it for me. Now moving the paper up and down is pretty easy. I'll feed the paper around a large roller, and have a couple smaller rollers hold the paper in place. Then I can rotate the rollers with a motor, and that will move the paper up and down. Moving it left and right is a little bit harder, but not by much. I'll just put the entire roller assembly on a linear bearing, and use another motor to slide that back and forth. And that should be everything I need. I can select the character I want, I can print it on the page, and finally I can move the page in both X and Y to the next position. So let's try it out. Yeah, and as you can see, this isn't quite right, although not actually as bad as it looks. Trying to type out the classic phrase, "the quick brown fox jumps over the lazy dog," and some of them, like this "the" here, and like the T at the beginning, and maybe fox, are looking kind of okay, but yeah. The good news, though, is that everything's printing along the same line, which means that it's just the yaw of the ball that's a problem, and that the tilting mechanism is working fine. So I'm going to go investigate that a bit further. If I try to wiggle the ball back and forth by hand, you can see there's a pretty decent amount of play in here. And this wasn't there when I installed this. So let me take this off and see if I can show you what the problem is. Alright, I'm not sure how well this is coming across on camera, but this is the dog bone here, and you can see that it's getting a little beat up. I had to trim down these just a little bit to get it to fit in there, but as that is, they're kind of too thin to provide much strength. So I think this is the issue. Now, unfortunately, there really isn't any room to make this this bigger or stronger, and I don't have a good way to make it out of metal, so I'm gonna need to try and find a different solution to this problem. My first thought was to get one of these flexible shafts that you'll use for like Dremels and multi-tool and stuff, but on the scale I need this to bend at, it's not actually quite bendy enough. A little too stiff here. So I tried to make my own flexible shaft, which got me this, which is far too springy. When more importantly, if I twist it, it just wobbles back and forth. Because nothing says precision like swobbling. Anyway, so after all that, I tried what you've probably been screaming at me this whole time to try, and I got a universal joint. Now, I had thought of this before, but I don't have much space inside the printhead. So if I want the ball to tilt properly, the central pivot of the U-joint and the tilt plate pivot have to be, collinear, which puts the pivot of the U-joint right here, inside this bearing, which has an inner diameter of 8 millimeters, while the U-joint has a diameter of 7. And this is the smallest one I could find. I can't use a bigger bearing because this is the biggest bearing I could find that fit inside the type ball. And this is when I had my big brain idea. What if I just delete the bearing? It's not like there's much load on it anyways, so I did exactly that. And it seems to have worked pretty well. The ball can fully tilt, and there's almost no play in it. So how well does this work? I mean, this is a bit better, but still awful. Yeah, this isn't any better. I mean, it's different, so I did something. The clearest part of this new one, I think, is maybe this fox right here, and even then, that's bad. And I really did go crazy trying to sort this out. Eventually, I decided to take a slow motion video of the thing typing. Now you see that frame right there. The type ball is hitting one of the ribbon guides, and that's knocking it out of alignment by just about half a character. Thankfully, that's an easy enough fix. I just need to make the ribbon guides a little bit wider, and it should be good to go. And with that done, let's see how it's printing. Well, that's a lot better. Obviously it's not perfect. I mean, you can see the vertical alignment on some of the letters here is off by a little bit. But the whole thing is legible, so I'm going to call this a win and keep moving on with this project. Now that it seems to be printing correctly, I wanted to actually use it as a typewriter for a bit. So I wrote some code which lets me use my computer as a keyboard. And I just type on the computer and it'll mirror what I'm typing onto the printer. And I can even correct myself. I mean, as long as that part hasn't printed yet. But I didn't just want to make a very loud computer-controlled typewriter. I wanted to use it to print pictures. And this brings us to the software. So, how do you print a picture with a typewriter? Let's say we have a low-resolution, black and white image we want to print, like this smiley face here. To print it out, it can just scan through the image, where we do nothing for the white pixels, and type a character for each black pixel. And for now, let's use the @ symbol. And we can see that this works, but only for fairly low resolution black and white pictures. Of course, most of the images we're actually interested in printing aren't just black and white, they're shades of gray, and they tend to be higher resolution than this. Give me a moment while I pull up a more interesting image. Now I can just threshold this into a pure black and white image, and do what I did before. But the output really just looks like gibberish. But I don't just have this one character, I've got 88 characters to work with. And we can calculate the apparent brightness of each of those characters by scanning them, and then looking at the average pixel values. For example, a lowercase a is much darker than a lowercase I. And if we do this for all the characters, we'll have a nice ranking from the lightest ones to the darkest ones. Then, for each region of the image, we can find that region's average darkness and put the appropriate character from our character set in its place. And this certainly looks a lot better than what we had before. It still doesn't look all that much like the original image. So I've just been kind of going at this, but let's take a step back and ask ourselves, what are we actually trying to accomplish with this? Well, we want to make the output image, which is made out of these text characters, match the original image as closely as possible. Now, so far, we've just been aligning the characters with some sort of grid, just like they'd be displayed on a computer. But this is a typewriter, and one of the big advantages a typewriter gives us is that we can place the character anywhere on the page. We're not constrained to rows or columns. But to take advantage of this, we'll need to take a different approach. Now we'll start with our target image on the left here, and our output text image on the right. To keep track of our progress, I'll add another image below the target image. This difference image shows the difference between our target image and our output image. For now, it's just a copy of our target image. To find the best place to put a new character, we can slide that character over this difference image and see how well it matches at each possible location. If we keep track of this match quality, we'll see a new image forming, where the brightest spot in this new image is the best place to put that character. So this is great, we found the best place to put this character. But this is just one of 88 characters. How do we know that this is the best possible character? Well, the only way to find out is to check all the other characters just to be sure. And only once we've done all of this can we finally add this best character to our image. And you can see that adding the character to our image changes the difference image. And so we'll just keep on doing this until it no longer improves our image. And as you can see, this works much better than what we had before. I mean, this output image looks pretty nice. But you might have also had the thought that isn't this really slow and a lot of computations? And you'd be right. See, this target image I'm working with is only about 500 by 300 pixels, but we're testing our character at each pixel, which is already 150,000 places to check. Then for each one of those checks, we're doing one computation for each pixel in the character image, which is 20 by 20. So that's 400 computations per check, which brings us up to 60 million operations per step. And of course, we need to do this for each one of our 88 characters, and that's over 5.2 billion computations, and all just for one character in the image. It ends up taking about 2,000 characters to make a good image, and this gives us a total of 10 trillion computations we have to do. Now, modern computers are really fast, but this is a lot even for them. So how can we make this faster? Well, remember how we're sliding the character over the difference image to make this match quality image? Now, if you're familiar with signal processing, you might just be thinking that sliding images over each other sounds suspiciously like a convolution. I mean, in fact, this is exactly what a convolution is. Yeah, so that's great, but how does calling it a convolution help? Well, convolutions come up all the time in image processing, so we've gotten pretty fast at computing them. And there's a really cool way we can do this that I want to tell you about. But for this to make any sense, I first need to tell you about the Fourier transform, and I promise this is relevant. A Fourier transform lets us represent any signal as a sum of sine waves, and any image, just like the one we have here, is really just another type of signal. When we put it through the Fourier transform, what we get back is known as a frequency domain image. The location of each pixel in this image represents a simple image made up of sine waves, one going in the x direction and one in the y direction. As the x index of our pixel increases, so does the frequency of the resulting x sine wave. And the same is true for y. To reconstruct the original image, we can take the sine wave image from that index and multiply it by the brightness of the corresponding pixel. Then, we go to the next pixel and do the same thing, adding the resulting images together. And as we keep doing this, we'll start to see our original image appearing. But what does this have to do with convolutions? Well, if we take the two images we want to convolve and then convert them into the frequency domain, multiply these frequency domain images together, and then convert back, that's the exact same thing as a convolution. And even though it's more steps, it's much faster. To put some numbers on it, my computer, it takes about 8.5 seconds per character to compute the direct convolution. But by using this Fourier transform-based convolution, it only takes 1/3 of a second to do the same thing, over 25 times faster. If you'd like to learn more about why this works, and take a much deeper dive into convolutions, 3 Blue 1 Brown has an excellent video you should check out. But for now, we've got a pretty good text image, and we won't dive old age before it computes. So, what are we waiting for? Let's get printing. I mean, hey, I never said this was going to be a good printer, but, for being a typewriter, I think this is really cool. Of course, I don't need it to use all the characters in every image. I could make an image out of just one character. And if I just use a period, well, it just became a bad dot matrix printer. In some ways this might actually be better. Although you can tell the ink ribbon got stuck right about here, so it's a little bit washed out. But what I think is a bit more fun than this, though, is I can actually make an entire image out of a single word. If you look closely at this one, you'll see that this picture of a dog is made out of the word dog. It's just dog, 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 dog. Yeah, you can see this image is just made out of the word dog, both horizontally and vertically. Anyways, this is all I've got for you today. Now, I'm sure there's more I could do with this machine, so if you can think of anything that you'd like to see, let me know in a comment. And as always though, if you enjoyed this video, I'd appreciate it if you give it a like. Now, if you want to see more like this, you can check out another one of my videos right here. I hope you enjoyed watching this as much as I did making it, and thanks for watching.